Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here. This is Andrew and Renee. Welcome to the Stack series. Today we are exploring chemical reaction networks, complexity, and the hidden structures that define how matter transforms. I was staring into my espresso this morning, really sort of looking into the depths of it, and I had this odd moment of realization.
Oh, yeah.
We walk through the world and we think of it as a collection of nouns, a cup, a table, a star, a person.
Objects.
Things. Exactly. But that's not right, is it? It's a kind of a comforting illusion. The universe isn't a museum of static things. It's this incredibly dynamic, chaotic, messy web of transformations.
It's all verbs.
It's all verbs. That star I'm looking at through the window isn't just there. It's actively burning hydrogen into helium. My stomach is right now dismantling this coffee into caffeine and hopefully some kinetic energy.
Right, and somewhere in a lab, a pharmaceutical company is synthesizing a molecule that simply did not exist anywhere in the universe yesterday.
It feels like we focus so much on the stuff, we completely forget about the happening, the transformation itself.
It's the classic philosophical distinction, isn't it? Being versus becoming. And you're right, for a long, long time, physics was obsessed with being, with describing the state of an object at a single point in time.
Pinning it down.
But the real magic, and certainly the real complexity, is in the becoming, in the transformation. And today, we're going to get into the language, the mathematical and physical language used to map those very transformations.
And the formal term for that is chemical reaction networks.
CRNs.
CRNs. It sounds a bit dry, I'll admit, a little sterile.
Sounds like a government agency that regulates food additives or something.
It does, but it's actually the bridge. It's the bridge between chemistry and, believe it or not, computation. It's how we shift our thinking from chemistry as cooking. A pinch of this, stir, heat to 350.
A bit of art, a bit of intuition.
To thinking about chemistry as logic. It's about understanding how matter itself computes its own future. And we have a pretty massive stack of research to get through on this. We're going to cover a lot of ground. We're going to start by looking at how pure graph theory, literally just drawing circles and arrows, can predict whether a chemical system is going to, say, explode or just peacefully settle down.
And it can do that without us knowing a single thing about how fast the reactions are, which is a deeply counterintuitive idea we really need to unpack.
Totally. Then we're going to get into what some are calling the active debate, which is all about artificial intelligence. You hear it everywhere. AI is going to solve chemistry, invent new drugs. But we have some fascinating papers here that suggest the AI might actually be, cheating on its chemistry tests.
Ah, the clever Hans effect. I love this part. It's a fantastic little detective story about how an AI can be right for all the wrong reasons.
And finally, we're going to touch on a really new, pretty mind-bending theory called assembly theory that might do nothing less than explain the origin of life itself. And on top of that, how we might one day detect alien life, even if it has absolutely nothing in common with us.
So yeah, it's going to be quite a journey.
Let's get into it. Okay, part one, foundations, what we think we know. If we really want to understand how the universe transforms itself, we have to start with the map. So walk me through the basic unit of a chemical reaction network. How do we even begin to draw this map?
The first step really is to unlearn what most of us learned in high school chemistry.
Okay, I'm ready.
In school, you learn stoichiometry. You learn A plus B equals C. It's linear. It's presented as a recipe. It's a one-way street.
Right. Vinegar plus baking soda equals a volcano for the science fair. End of story.
Exactly. But inside a living cell or in a planet's atmosphere or in a huge vat of industrial chemicals, you never ever have just A plus B equals C.
It's never that simple.
Never. You have A plus B making C, but at the same time, C is degrading back into D, and maybe D is interacting with the original A to create E, and then E turns around and acts as a catalyst for the first reaction, making it go faster.
So it's not a line, it's a hairball. It's a tangled mess.
It's a network, a dense interconnected web. And to make any sense of that hairball, scientists use a branch of mathematics called graph theory.
Circles and arrows.
The very same. And in the sources we're looking at today, particularly the foundational work on something called Deficiency Zero networks, they break the network down into three core components. You have the species, the complexes, and the reactions.
Okay, let's break those down one by one. Species seems easy enough. That's just the chemicals, right? The ingredients.
Correct. Those are the nodes in your graph. Hydrogen, oxygen, glucose, some specific protein. They're the players on the field.
Got it. And the reactions, I'm guessing, are the arrows, the lines connecting the nodes.
Yes. Those are the edges of the graph, the transformation itself. the action. But the middle one, complexes, that's the subtle one that can trip people up at first. A complex isn't just a single chemical.
Okay.
It's the collection of species on either side of the reaction arrow.
Give me an example of that.
Sure, let's take the classic reaction. 2 molecules of hydrogen plus 1 molecule of oxygen transforms into 1 molecule of water.
H2O. Got it.
In that reaction, the phrase 2 hydrogen plus 1 oxygen is a complex. It is a distinct state of matter. It's the before state.
A collection of things waiting to react.
Exactly. And the water, on the other side, is the after complex. So the reaction arrow isn't just connecting hydrogen to water. It's connecting the state of being 2 hydrogens and an oxygen to the state of being water.
Okay, so why is that distinction so important? It feels a little academic.
Because it allows us to map the entire system like a subway map. It's the best analogy I've
The
found.
subway map. I like that.
Imagine the complexes are the stations. So Grand Central is the state, 2 hydrogens and an oxygen. And Times Square is the state, water. The reactions are the tracks connecting the stations, and the species, the individual chemicals, they're the passengers riding the trains.
Okay, that clicks. So the questions a chemist asks are things like, can I get from Grand Central to Times Square? Is there a track? Is it a one-way track, or can I take a train back?
Is it an express track or a local? Does it form a loop?
Oh.
That's what network analysis is all about.
And this brings us right to one of the biggest problems in actually simulating chemistry, right?
Yeah.
Because to make a useful subway schedule, I don't just need the map. I need to know how fast the trains are moving.
Right. And you've just landed on the domain of kinetics. To model a system in the traditional way, you absolutely need what are called rate constants.
The speed limits.
It's the speed limits for every single reaction. You need to know exactly how many milliseconds it takes for protein A to find and bind to protein B inside a crowded cell. And then you need to know how that speed changes if the temperature drops by half a degree or if the pH shifts slightly.
I'm going to go out on a limb and say that measuring thousands of those individual speeds inside a living, squishy, constantly changing cell is difficult.
It's a complete nightmare. It is, for all practical purposes, impossible to get a full, accurate set of rate constants for the thousands of reactions happening in a single cell at any given moment.
So that's the wall. That's why systems biology is so incredibly hard. We have the map, but we have no idea what the speed limits are. We're kind of stuck.
We were stuck. Or at least it looked like an intractable problem, until the mathematics of topology, the study of the shape itself, came to the rescue.
Shape of the map.
The shape of the map.
Right. Yeah.
In the 1970s, researchers like Martin Feinberg and Horn and Jackson developed something that is now known as the Deficiency Zero Theorem.
Deficiency Zero Theorem. It sounds like a medical diagnosis. Good news, your tests came back. You have zero deficiency.
It's funny you say that because in this context, it's actually the holy grail of stability. It's the best diagnosis you could hope for. The theorem asks a really radical question.
Which is?
Is it possible that the shape of the network alone, just the pattern of stations and tracks, could guarantee that the system will be stable, regardless of how fast the trains are moving?
Whoa, okay, hold on. That sounds like magic. That's like saying, I can guarantee you won't ever crash your car, no matter how fast or slow you drive, just because of the layout of the city streets.
That is essentially the claim. It's an incredibly powerful idea, but of course the road network has to have a very, very specific shape.
Okay, so what is that shape? The theorem says if a network meets certain conditions, it's guaranteed to be stable. Let's drill down on that. What's condition number 1?
The network must be weakly reversible.
Weakly reversible. Okay, what does that mean? Does it just mean every reaction can go backwards? Like I can unburn a piece of toast?
Not quite, and that's a key distinction. It doesn't mean that every single arrow on your map is a two-way street. What it means is that the graph as a whole is connected in a way that there are no dead ends.
On terminal stations.
No terminal stations. If you can get from state A to state B, there must exist some path. It could be incredibly winding and complex and go through 20 other states, but there must be some path that eventually leads back to state A.
So everything is part of a cycle, or a series of interlocking cycles. It's a closed loop of flow.
Exactly. Nothing can get stuck in what's called a sink, where it just piles up forever and is removed from the system. Everything eventually gets recycled.
Okay, that makes a kind of intuitive sense, especially for biology. Life is a cycle. So that's condition 1. What's the second condition? The deficiency zero part of the name.
This is the harder concept to build intuition for. The deficiency of a network is a specific number. It's a geometric property that you calculate.
How do you calculate it?
Well, the formula is the number of complexes, the stations, minus the number of connected components in the graph, minus the rank of the reaction matrix.
Okay, you're losing me with rank of the reaction matrix. Can you give me the intuition behind it? What does deficiency mean?
Think of deficiency as a measure of the network's independence, or maybe its looseness. In any chemical network, the reactions are constrained by the conservation of atoms. You can't just create matter out of nowhere.
Right, the books have to balance.
The books have to balance. A network with zero deficiency is one where the reactions are very tightly coupled. The mathematical logic of the connections is rigid and disciplined. The constraints of conservation are very strong.
And a network with a higher deficiency
is floppier. The reactions have more freedom to move independently of the nodes. There's more wiggle room in the system's logic.
So deficiency zero essentially means the network is mathematically disciplined. It's rigid in its structure.
Geometrically disciplined is the perfect way to put it.
So let me see if I have this right. If I have a chemical network that is a closed loop, so it's weakly reversible, and it's geometrically disciplined, so it's deficiency zero, what happens? What's the grand prize?
The theorem guarantees with mathematical certainty that there is one and only one equilibrium point for that system, a single stable state. And this is the absolute kicker. The system must find it.
It must find it. It can't get lost.
It is precluded from exhibiting chaos. It's precluded from having wild, sustained oscillations where the chemical concentrations swing up and down forever. The very structure of the network forces it to settle down into a single, predictable, steady state.
And it does this regardless of the rate constants. That is the part that just keeps blowing my mind. You could heat the system up, cool it down, throw in an enzyme that speeds one reaction up 1,000,000 times, and it will still find its way to that same stable point.
Correct. The analogy they use is a ball rolling into a bowl. It doesn't matter where on the rim you drop the ball. It doesn't matter if the ball is heavy or light. It doesn't matter if you grease the inside of the bowl or line it with sandpaper to change the speed.
The shape of the bowl is what matters.
The shape of the bowl forces the ball to the bottom every single time. The stability isn't in the kinetics, it's not in the chemistry, it's in the geometry of the network.
So the sources we looked at describe this as a potential gift of evolution. What do they mean by that?
Well, think about it. If you're a primitive cell trying to survive on a chaotic early Earth, what's the environment like?
A total mess. Temperatures are swinging wildly, the pH of the water is changing, nutrient availability is unpredictable.
Exactly. Chaos. If your internal metabolism, your very survival, depended on all your thousands of reaction speeds being perfectly tuned to one another, you'd be dead in 5 minutes.
The first cold front would kill you.
You need a system that is robust against that external chaos. You need your metabolism to be a bowl, not a razor's edge. So nature would naturally select for networks that have this deficiency zero property.
So evolution isn't just selecting for, say, better enzymes that work faster. It might be selecting for better graph topology, a better network map.
That's the argument. It's building a house that is architecturally forbidden from collapsing rather than just trying to make the bricks stronger. The stability is an emergent property of the whole system's design.
That is a really profound shift in perspective. It's not about the players, it's about the rules of the game they're forced to play.
And this leads us directly to the next question. How do we measure the complexity of these rules? This brings up the idea of information theoretic network complexity.
Which sounds like we're taking chemistry and plugging it directly into computer science.
That's exactly what's happening. Researchers are now using tools like Shannon entropy. This is the same mathematics Claude Shannon developed to measure information in telephone signals, the same math that underlies data compression and the entire internet.
And they're applying it to chemical graphs. Usually I think of entropy as a measure of disorder or maybe surprise in a message.
And in this context, it's used to measure heterogeneity. How different are the various parts of the network from each other? Are all the nodes connected in the same boring, repetitive lattice structure?
Like a simple grid of city streets.
Or is there a rich hierarchical structure? Does it have major hubs with lots of connections and smaller spokes that are less connected? Is it more like the airline route map or the neural network of a brain?
And you can quantify that difference.
You can. They use things called topological indices to assign a single number to these incredibly complex structures. You can literally calculate how complex a chemical system is just by analyzing its map. You don't need to see the chemicals bubbling in a flask. You just look at the drawing.
Okay, so that's our foundation. Chemistry isn't a recipe, it's a graph. If that graph has a specific shape weakly reversible and deficiency zero, it is inherently robustly stable. And we can measure its structural complexity using the tools of information theory. That's the elegant mathematical ideal.
That is the clean blackboard version of reality, yes.
But now we have to leave the blackboard and enter the messy, real world of modern technology. Which brings us to part 2, active debate.
This is where things get really spicy.
We're living in the age of AI. I mean, it's everywhere. ChatGPT, AlphaFold, you name it. And there's this pervasive assumption that AI is just going to solve science for us. Just ask the computer to invent a new cancer drug and come back tomorrow.
The black box approach to discovery. You feed it a mountain of data, you turn the crank, and a miracle comes out the other side.
But one of the key papers in our stack today throws a massive, massive wrench in that machinery. It suggests that when it comes to chemistry, our best AIs might be acting a lot like a character from the early 1900s named Clever Hans.
I absolutely love that they use this analogy in a formal, peer-reviewed chemistry paper. It's so perfect.
So for our listeners who might not know the story, who was Clever Hans?
Hans was a horse in Germany around the turn of the 20th century. And by all accounts, Hans was an absolute genius. His trainer, a man named Wilhelm von Osten, would ask him math questions in front of a crowd.
Math questions. To a horse.
Oh, yes. Hans, what is 2 plus 3? And Hans would tap his hoof on the ground 5 times. He could do fractions, he could tell you the date, he could read a clock. Scientists at the time were completely baffled.
I would be too.
Until a skeptical psychologist named Oskar Funkst decided to run a very carefully controlled experiment. And he noticed something crucial. Hans could only answer the question correctly if he could physically see the person who was asking it.
So he wasn't actually doing math in his head?
Not at all. He was an expert at reading human body language. Funkst discovered that as Hans started tapping his hoof, the person asking the question, the trainer, a scientist, anyone would tense up in anticipation.
Leaning in.
Exactly. And when Hans reached the correct number of taps, say 5, the person would involuntarily relax. Their posture would shift slightly, maybe they'd exhale, or their head would dip just a millimeter. Hans would see that tiny unconscious cue and know it was time to stop tapping.
So he wasn't solving the problem, he was just reading the room.
He was getting the right answer for completely the wrong reason. A brilliant trick, but not mathematics.
So how on earth is a supercomputer at Google or somewhere running a state-of-the-art AI acting like that horse?
The researchers in this paper analyzed a model called the molecular transformer. This is a massive deep learning model, very powerful, designed specifically to predict the outcomes of chemical reactions. You feed it the ingredients, the reactants, and it predicts the product.
And how good is it?
On the surface, it's amazing. It's about 90% accurate on the standard benchmark tests.
90% is an A-. I'd take that in any chemistry class I ever took.
It looks fantastic. But these researchers decided to do what Oskar Funkst did. They decided not just to look at the answer, but to interrogate why the AI was giving that answer. They focused on a very specific, very famous class of reactions called Friedel-Crafts oscillations.
Okay, let's slow down and really unpack the chemistry here so we all understand what's at stake. Friedel-Crafts, what is happening in that reaction?
It's a cornerstone of organic chemistry. The basic idea is you have a benzene ring, which you can picture as a simple hexagon of carbon atoms, and you want to attach a new group of atoms onto one of the corners of that hexagon.
Okay, I've got my hexagon. I want to decorate it.
Perfect. Now here's the fundamental rule of this kind of chemistry. If there is already something attached to one of the corners of that ring, that existing group acts like a director or a gatekeeper. It dictates where the new group is allowed to sit. This is a concept called regioselectivity.
I like using a dinner table analogy for this. If I'm already sitting at a round table, I get to influence where the next guest sits. I might say, you can't sit next to me, you have to sit directly across from me.
That's a perfect analogy. And in the specific experiment the researchers ran, the gatekeepers already sitting at the table was a fluorine atom.
Fluorine.
Now, from a century of physics and chemistry, we know exactly what fluorine does. It's the most electronegative element there is. It's an electron hog. It powerfully sucks electron density from the ring towards itself.
So it changes the electrical landscape of the whole hexagon.
Dramatically. And because of that fundamental physics, it directs any new group to a very specific spot, the para position. The seat directly across the dinner table.
Okay, so the laws of physics are unambiguous. If fluorine is the gatekeeper, the answer is para. End of story.
Correct. So the researchers gave this exact problem to the AI. Here's a benzene ring with a fluorine on it. We're going to add this other group. What is the product?
And the AI said?
The AI said the product is para.
It worked. It got the right answer.
It got the right answer. But
Right.
then came the clever part. The researchers used a diagnostic tool called integrated gradients. You can think of it like an MRI for the AI's decision-making process. It generates a heat map that shows which parts of the input molecule the AI was paying the most attention to when it made its prediction.
So if the AI actually understands chemistry, that heat map should be glowing bright red right on top of that fluorine atom. It should be thinking, aha, fluorine. That is the causal reason I must choose para.
That's what you would expect. That's what a human chemist would do. But when they looked at the AI's heat map, the fluorine atom was completely dark, blue, cold. The AI assigned it an important score of basically 0.
Wait, it completely ignored the fluorine, the single most important atom that actually dictates the entire outcome of the reaction.
It ignored it completely.
Then how in God's name did it get the right answer?
This is the clever Hans moment. This is the big reveal. It turns out the AI was trained on a massive database of millions of chemical reactions, most of them scraped from patents filed by chemical companies over decades. And in the history of human chemistry, when chemists perform this type of reaction, they're almost always trying to make the para product for practical reasons. It's the most common, most useful outcome. So about 90% of the examples in the training database were, in fact, para products.
Oh no. So the AI didn't calculate the electron density of fluorine. It just looked at the problem, recognized the general pattern, and said, well, in the big book of answers I studied, the answer to this kind of question is usually para. So I'm just going to guess para.
It played the odds. It wasn't learning the laws of physics. It was learning the statistical bias of the data set.
That is just wild. It's like a student who doesn't study for a multiple choice math test, but he knows from past experience that this particular teacher usually makes the correct answer C. So he just bubbles in C for every single question and ends up with a passing grade.
That is exactly what is happening here. And the researchers didn't just suspect this, they proved it. They set a trap for the AI.
Ooh, I love a good trap.
They dug through the literature and found a set of very rare, unusual reactions, ones that were not common in the patent database, where the real chemistry, the physics, dictates that the product should be meta, not para, a different seat at the table.
The unpopular answer.
The unpopular answer. And they gave these problems to the AI, and what do you think it did?
It still guessed para.
It failed miserably. It kept guessing para because it had no concept of why the answer should change. It was just hallucinating the most popular answer from its memory, completely blind to the actual physical reality of the molecule in front of it.
This connects directly to another key concept they talk about in the sources, scaffold bias.
Yes. This is the underlying mechanism that explains why the AI looks so smart on paper and why its 90% accuracy score is so misleading.
The scaffold is the core structure of the molecule, right? The carbon skeleton.
Exactly. And in machine learning, the standard practice is you take your huge data set and you split it. You use most of it as a training set. That's what the AI studies. And you hold back a small portion as a test set. That's the final exam to grade its performance.
Standard procedure.
But the researchers found that in the standard chemistry databases, the molecular scaffolds in the test set were almost identical to the scaffolds in the training set. There was huge overlap.
So it's not just testing on easy mode. It's testing on the exact same questions it studied. So like if I give you 10 math problems to study and then the final exam is just those same 10 problems with the numbers slightly changed.
Precisely. So the researchers did something different. They performed what's called a Tanimoto split.
That sounds like a judo move, a Tanimoto split.
It's a much more rigorous way of separating the data. They used a similarity metric to ensure that the chemicals in the test set were structurally different, that they had genuinely new scaffolds from the ones the AI had seen in training. They forced the AI to generalize its knowledge, to apply its logic to a truly new situation.
And what happened to that shiny 90% accuracy score when they did that?
It plummeted. It dropped all the way down to about 74%. And in some specific, more challenging categories of reactions, it was even lower.
That is a very sobering reality check for the whole field.
Like huge. It reveals that we are very likely overestimating our ability to automate chemical discovery. We haven't built a chemist in a box. We've built models that are excellent librarians. They are incredibly good at retrieving known patterns from the vast archives of human patent literature.
But they're terrible physicists. They don't actually understand why matter transforms the way it does.
They're just clever Hans tapping their hoof because they sense what we want the answer to be.
And this is a massive problem if our goal is to discover truly new science, right? If the AI only knows what we've already done, it's just going to keep giving us slightly different versions of the same old stuff.
It's the echo chamber of discovery, and we'll get into the huge economic implications of that later on.
This feels like a perfect pivot point. We've established that simple pattern matching isn't enough to understand complexity or predict reality. We need a deeper theory. We need a fundamental way to distinguish between a random, jumbled mess and a genuinely constructed, complex object.
Which brings us to part 3, frontiers. And this is where we get into the really big ideas, specifically a new framework called assembly theory.
This is the work heavily associated with people like Lee Croman and Sarah Walker. And I have to say, reading through these papers, this is the part of the stack that feels the most revolutionary. It feels like they're trying to write a new law of thermodynamics or a new law of information.
They effectively are. They're trying to solve a problem that has secretly plagued science for centuries, which is, what is the actual measurable difference between something that is complex and something that is just random?
Right. It's an intuitive difference. If I spill a bag of Scrabble tiles on the floor, the resulting pattern looks chaotic and random. If I arrange those same tiles to spell out a sonnet by Shakespeare, it's clearly complex. But how do you put a number on that difference?
Cronin and Walker's big idea is that you measure it by its history.
Its history. Explain what that means.
They introduce a new quantity called the assembly index. The idea is this. Imagine you want to build a molecule, or any object. The assembly index is the minimum number of steps, the shortest possible construction path required to build that object from its most basic, indivisible building blocks.
Okay, let's use a Lego analogy. If I have a single 2x4 red brick, that's a basic block. Its assembly index is effectively 1 or 0. It just exists.
Right. If you take a blue brick and stick it on top of the red one, that's one assembly step. The resulting object has an index of 1. Now imagine you want to build the giant 1,000-piece Lego Millennium Falcon set.
It's a lot of steps, a lot of history.
It's a very specific sequence of steps. You can't just shake the box of 1,000 Lego pieces for 1 billion years and expect the Millennium Falcon to pop out fully formed.
No, of course not. The number of incorrect ways to put those pieces together is astronomically larger than the 1 or 2 correct ways described in the instruction manual.
Exactly. And this is where the mathematics of assembly theory gets truly terrifying and awe-inspiring. They calculated the size of what they call the assembly universe. As you add more parts, as the molecule you're trying to build gets bigger, the number of possible combinations grows double exponentially.
Double exponentially. That's not a term you hear every day. It's not just a steep curve.
It's a vertical wall. It grows so fast it's almost unimaginable. They showed that by the time you get to a molecule with just a moderate molecular weight, something like a small protein or a complex drug like Taxol, the number of possible ways to arrange those atoms is larger than the number of atoms in the entire known universe.
Okay, can you just pause on that for a second? The number of potential molecules of a certain size is larger than the number of atoms available in the entire universe to build them with.
Yes, and this implies something incredibly profound. The universe is not big enough and has not existed for long enough to make these complex things by random chance. It's not just improbable, it's physically impossible. There hasn't been enough time or matter to even try a fraction of the possibilities.
So, if I find a high assembly molecule, if I'm an astronaut and I find the Lego Millennium Falcon just sitting on a rock on Mars,
it proves with mathematical certainty that selection occurred. It's absolute proof that there was a system, a machine, a living cell, a chemist, an alien that possessed the information or the memory needed to navigate that impossibly vast space of possibilities and follow a specific construction path. Chance is ruled out.
So the assembly index, it's a lie detector for life. Or for intelligence.
It is. It's a way to define the signature of life without ever mentioning biology. You don't need DNA, you don't need cells. Life is the process that can access the deep, high assembly parts of the universe. It is the mechanism that selects a specific, rare history from an ocean of random noise.
That's beautiful. The complexity of an object isn't a property of the object itself in the present moment. It's a measure of the memory of how it was made.
Yeah. And this connects directly to the biggest question of all, the origin of life. We have this huge, mysterious gap in our understanding. On one side, you have dead prebiotic chemistry rocks, water, simple atmospheric gases, low assembly stuff. On the other side, you have biology cells, DNA, complex proteins, high assembly stuff. How do you build a bridge across that canyon?
The sources mention something called the assembled world hypothesis.
Yes. It suggests that we shouldn't be looking for a single magic spark or a magic molecule that suddenly came to life. We should be thinking about it as a continuum, a gradual journey of increasing assembly index, passing through different worlds.
Walk us through these worlds.
Well, you start in the environmental world. Simple physics and chemistry dominate. Everything has a very low assembly index. Then, as complexity starts to build, you might enter the cellular world,
It's like viruses.
or things that behave like viruses. Self-replicating packets of information that aren't quite alive in the traditional sense, but they are demonstrably climbing the assembly ladder. They are storing and using historical information. And then, somewhere in between that and true cellular life, there is what the authors call the mysterious earthly place.
The MEP.
The great unknown zone, the transition where these chemical networks we talked about in part 1 became fully self-sustaining. The point where the topology, perhaps a deficiency zero topology, locked into place and created a stable replicating system.
So life isn't a substance. Life is a network state, a particular kind of topology that matter can adopt.
Precisely. It's what physicists call a non-equilibrium steady state, or an S.
We should probably unpack that term as well, non-equilibrium.
Okay. Think of a whirlpool and a river. Does a whirlpool exist? Is it a thing?
Of course. I can see it. I could point to it. I can get my boat stuck in it.
What is it made of?
It's made of water.
But the individual water molecules that make up the whirlpool 1 second are gone the next, swept downstream. New water is constantly flowing in to take their place. If you stop the flow of the river, if the river reaches thermal and chemical equilibrium, the whirlpool vanishes.
It's a stable structure that's only maintained by a constant flow of energy and matter through it.
That is what you are. That is what a cell is. You are a very, very complex whirlpool. You are taking in food and energy. You are dissipating waste and heat out into the environment. And by doing so, you maintain your complex high assembly structure against the relentless pull of the second law of thermodynamics, which wants to turn you back into dust.
And the sources say there's a kind of emergent second law for these non-equilibrium systems.
That's a frontier of research, yes. The normal second law says that in a closed system, entropy disorder always increases. But for these open, steady-state systems like life, new thermodynamic laws seem to emerge that describe how they maintain their order, but always at a cost.
This is the thermodynamic cost of living. Being alive is energetically expensive.
Incredibly expensive. And the more complex the network, the higher its assembly index, the higher the energetic cost to maintain its structure against decay.
Okay, so a clear picture is starting to form.
Mm-hmm.
Life is a high-assembly, non-equilibrium chemical network. It's likely built on a stable topology, like a deficiency zero network, that requires a constant flow of energy to persist. And it's fundamentally built on a history of selection, not random chance.
That's a fantastic summary of where the cutting edge of biophysics and complexity science is heading.
So now for the big question, what do we do with this knowledge? This brings us to part 4, implications.
And this changes our thinking about everything from medicine here on Earth to how we search for life in space.
Let's start with space. We use the analogy of finding a complex Lego set on Mars. How does assembly theory change the practical search for alien life?
Right. For decades, agencies like NASA and ESA have been obsessed with finding biosignatures. But traditionally, they look for things that resemble life on Earth. They look for specific amino acids or evidence of liquid water or complex carbon molecules that look like fragments of DNA.
Which is a huge assumption that alien life would be just like us, just with green skin.
It's an incredible bias. Assembly theory provides a way out. It says, stop looking for the specific materials of life. Start looking for the mathematical signature of its complexity.
So what does that look like in practice?
You send a mission with a mass spectrometer to a place like Enceladus, one of Saturn's moons that we know has a subsurface ocean. You scoop up some of the ice that's been ejected into space, you vaporize it, and you measure the mass of the molecules inside. If you find a molecule with a calculated assembly index of, say, 15 or 20 or higher,
It doesn't matter if it's made of carbon or silicon or some kind of plasma.
it doesn't matter at all. If the index is that high, you can say with near absolute certainty that it could not have formed by random geological or chemical chance. You have found definitive evidence of a process of selection. You have found alien life, or at the very least, alien technology.
That feels like a much more robust, less biased way to hunt for life.
It's physics-based life detection, not biology-based. It's a universal standard.
So what about the implications back here on Earth? Let's go back to drug discovery. We talked about the AI being trapped in an echo chamber. What's the danger there?
The economic danger is immense. Pharmaceutical companies are pouring billions and billions of dollars into AI-driven drug discovery. But if the AIs are all clever Hans, if they're all biased towards what we've done before, like in the Friedel-Crafts example, then we're just going to rediscover variations of aspirin for the next 50 years.
We'll get really good at finding molecules that look almost exactly like the ones we already have patents for.
Exactly. And to use a music analogy, it's like we'll never discover techno or hip-hop. We'll just keep getting slightly different remixes of the Beatles. But the cure for Alzheimer's might be techno. It might be a completely novel molecule with a scaffold that human chemists have never seen before. A high-assembly object that a biased AI would look at and think is wrong or unlikely, simply because it isn't in its training database.
So the fix is that we need physically aware AI.
We need AI that understands the fundamental rules, the quantum mechanics, the electron orbitals, the thermodynamics, the assembly pathways, rather than just memorizing the statistical outcomes from a biased historical record. We need an AI that can actually navigate the vast assembly universe for real, not one that has just memorized the map of the tiny part of it we've already explored.
And finally, let's talk about the frontier that feels the most like science fiction, reprogramming matter.
This is the ultimate goal, isn't it? If life is just a special kind of chemical network, a form of computation, can we hack it? Can we become programmers of matter?
The idea of algorithmic complexity.
There's a lot of research now into designing what are called autocatalytic sets. These are chemical networks that are designed to make themselves. You have molecule A, which catalyzes the formation of B, B catalyzes the formation of C, and C comes back around and catalyzes the formation of A.
A self-sustaining loop.
A closed, self-sustaining loop. If we can truly master the design of these loops, if we can write the source code for a chemical network from scratch, we can create genuine synthetic life. Not just artificial intelligence in a computer, but artificial life in a test tube. Materials that can heal themselves, vats of goo that can perform computations.
But the sources also sound a pretty strong ethical warning here, don't they?
A huge one. Remember the gift of evolution from part 1? Those robust, stable, deficiency zero networks?
Right, the ones that are naturally stable because of their shape.
Evolution spent 4 billion years beta testing those networks. It ran an uncountable number of simulations, and it found the architectures that don't crash. It debugged the system.
And here we are, trying to write new biological code on a Tuesday afternoon in a lab.
Precisely. If we build these new synthetic biological networks, they might be incredibly efficient at doing the one thing we designed them for, but they might be incredibly fragile. They might lack that evolved deficiency zero robustness.
So we could create a synthetic bacterium that, say, eats plastic, and it works great in the controlled environment of the lab. But the moment it gets out into the real world, with fluctuating temperatures and pH,
it could hit a condition it wasn't designed for and suffer a catastrophic failure. A biological blue screen of death. Or, even worse, it could crash the ecosystem around it because it doesn't play by the established thermodynamic rules of the neighborhood.
it feels like the stakes are that we are literally writing new laws of nature. And we'd better make damn sure we don't have any typos in our code.
We have to understand the thermodynamic cost of our creations. It all comes back to that. Nothing in the universe is free. If you want to build and maintain a complex, high-assembly object, you have to pay for it with energy. We need to be responsible for the energy budgets of our inventions.
It really does feel like we are standing on the cusp of a new era. We're transitioning from being passive observers of chemistry to becoming active programmers of chemistry.
We are finally truly internalizing the idea that the universe is computable, that matter is just the hardware, and the laws of these reaction networks are the software. And we, as a species, are just now learning how to type our first hello world.
That is a thought that is both incredibly exhilarating and, frankly, a little bit terrifying.
As it probably should be.
So I guess the next time I'm staring into my coffee, I'm not just going to see a brown liquid. I'm going to see a high-assembly, non-equilibrium, potentially deficiency zero network of ongoing transformations.
And you'll probably let it get cold while you're thinking about all that.
Almost certainly. Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support. And to our listeners, thank you for being part of this journey with us. If you enjoyed today's episode, be sure to subscribe and follow Stack Studios for more informative content and support us on Patreon. Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.